Good morning students. In this video we can discuss about how to convert from push down automata to their equivalent context free grammar. Otherwise we can construct context free grammar from the given push down automata. So here the question is construct a CFG equivalent to the following push down automata. So that means here it was given some push down automata and then now we will try to convert into their equivalent context free grammar. So here the push down automata contains these are the several transitions. So that is del of p comma 0 comma z is equals to p comma xz, that is push operation. And next del of p comma 0 comma x is equals to p comma xx, this is also push operation. And next del of p comma 1 comma x equals to q comma epsilon, so that is pop operation. And next del of p comma 1 comma x equals to p comma e, so this is also pop operation. And next del of p comma epsilon comma z equals to p comma epsilon, so this is also pop operation. So here when already in last video we was discussed, while we will go for conversion from push down automata to context free grammar, push operation or push instruction can require four production rules to convert into context free grammar. So here 4 was not fixed based on the number of states and then number of states. So here number of states is 2, p and q, so that's why it requires 4. In case 3 states, then 9 production rules was required to conversion from push down automata to context free grammar. So that's why for first production rule we can construct 4 production rules. First transition, for second transition we require 4 production rules, and then for remaining 3 we require exactly 3 production rules, totally 8 plus 3 plus 2, so total 13 productions will be required. So now we observe how to now we can proceed how we can convert from push down automata to their equivalent context free grammar from each and every production rule. So while we will go for converting into context free grammar, first of all we assume there is some context free grammar G, so which is equals to 4 tuples, those are V, T, P, S. So from here we can assume whatever the each and every symbol, for example terminals is nothing but whatever the input alphabet from the push down automata, those are 0 comma 1. So here given was 0 comma 1, so that's why T equals to 0 comma 1 and S equals to, here it was clearly given, so that is P. So here starting state is P, so that's why starting symbol is equals to P. So here this is the starting state or initial state, that is P, so that's why here starting state is P. So S equals to P. And next V, set of non-terminals, so that is we consider from whatever the default top of the stack symbol, that is Z, or starting symbol of the stack, that is Z, and then all possible combinations with each and every state PQ. So that's why P comma Z comma P, P comma Z comma Q, in this manner we can consider all possible non-terminals. Now we can convert from push down automata to their equivalent context free grammar. So already in last session we was discussed how to convert from push down automata to context free grammar by using 3 rules. One is for starting symbol, whatever how we can generate the production rules, for push operation how we can generate the production rules, and for pop operation how we can generate the production rules, and also no operation also. So here first we can build production rules for the starting symbol. So here starting symbol is P, so that's why we can start with starting symbol as P, and top of the stack or starting symbol of the stack is Z, so that's why we can consider as P comma Z comma, possible next state is any one of the given set of states. So here given that 2 states, that's why one time we can consider next state as P, another time we can consider as next state as Q. So here starting state is same, fixed, P is the starting state, and empty stack or top of the stack, first symbol of the stack is Z, and whenever we read from current state P, top of the stack is Z, or stack symbol is Z, then go to next state as P or either Q. So that's why we consider 2 production rules for the starting symbol. Next step. So we consider each and every every transition and then convert into their equivalent production rules. So now we consider first production rule. So that is del of p comma 0 comma z is equals to p comma xz. So this is given data. So del of p comma 0 comma z equals to p comma xz. So here to convert into production rules, we can assume current state is p and RHS first state is also p, and maybe next state is one time we can consider as p, another time we can consider as next state as q. So that's why here current state is p and next state possibilities are 2. So that's why total 4 combinations will occur. So that's why we can assume current state is p and top of the stack, this is the top of the stack z. So top of the stack is z, and then go to next state as p. So then input is 0 from here. So this is the input is 0, and then go to next state as p. So here it was mentioned p. So that's why p, and stack symbol is x. We can consider from here RHS stack symbol is x, and next state may be p. So that's why next state is p. That's why next we can consider again from p state, and next top of the stack or next stack symbol is z, and then go to next state is p. So here these two is always matched. These two is always matched, and these two is always matched. So here this state is our assumption. One time we can consider one state as next state, another time another state as next state. So this time we can consider p as the next state. Next time we can consider q as the next state. That's why p comma z comma p. So same input current state is same, top of the stack is same, and next state is same. But our assumption is input is also same 0. So here this state is also fixed for all 4 production rules, and currently top of the stack is x, and then now we assumption next state as q. Current state p, top of the stack is x, and the next state we assume either q. So then we can read next top of the stack is also from the same state q, and top of the stack is z, and then go to next state as p. So next we assume, so here next state is p, here next state is q, same combination. So that's why p, z, next state is our assumption is q. So that's why input is 0, and current state is p, top of the stack is first stack symbol x, and next state our assumption is p. So that's why again we can consider from state p, next top of the stack is z, and then go to next state as q. So it was wrong, this is q, it's not p. So this is q, which was mistake. So this is q, it's not p, it is q. So these both will be must be matched. Next, so at the same way input is p, top of the stack is z, and next state is same q. So here we can assume next state as q, remaining is same as it is 0, p, currently top of the stack is x, and next state is our assumption q. Next we can start next top of the stack from the same state q. So that's why here also q, and top of the stack is next stack symbol is z, and next state is these two must be matched. That's why we can assume q. So these are the 4 production rules from the first transition, del of p comma 0 comma z equals to p comma xz. This is push operation, and in this transition contains, sorry, in this push down automata contains totally 2 states. Number of states is 2. That's why 4 combinations will occur. Next we consider second transition. So that is del of p comma 0 comma x equals to p comma xx. So here current state is p, and input symbol is top of the stack is x, sorry, input symbol is 0, top of the stack is x, and then go to next state as p, and perform the push operation. So that's why it was also generates the 4 production rules. So we are starting from the current state p, current state is p. So in 4 production rules current state is fixed, and the next state is sometime one time we assume next state as first state p, and another time we assume next state as another state q. So and then here whatever the input, so that input can be written after arrow arrow mark. So here this input can be right here. So this input can be right here, and this state is as it is P, and currently top of the current stack symbol is X, and then here next state, this is our assumption. One time we assume P, another time we assume Q. So that's why this time we assume P. So that's why next state is also same P. We read another stack symbol and then go to next state as P. This was fixed. Why? Because here next state is P. So that's why both will be same. At the same way, next also we consider same combination. So P comma X comma, so P comma X comma P. So here current state is P, top of the stack is X, next state is also P. So that's why here input is as it is, initial state is as it is. So first stack symbol is X, and next state, so when read P X, when read top of the stack X from initial state or from state P, then go to next state as Q. So that's why here also we assume Q to read next stack symbol. So that's why Q comma X comma P. So this P is fixed. Why? Because already here next state is P. That's why. So this is the combination. So next current state is P, and top of the stack is X, and next state is Q. So here input is fixed 0, initial state is P fixed, and currently top of the current stack symbol is X, and next state is our assumption, one time P, another time Q. So that's why here also same combination. So here next state is our assumption P. That's why here now current state is P for read next top of the stack. Here our assumption next state is Q. So that's why next to read another stack symbol from the Q only. So that's why these two are fixed. These two are same, and these two are same. This is our assumption. Here we assume next state as P. Here we assume next state as Q. And this one can be decided on the from here. So here next state is Q. So that's why finally next state is Q. Here next state is Q. That's why finally next state is Q. So these are the 4 production rules generated from the second transition, from this transition. And next production rule is pop operation, that is del of P comma 1 comma X equals to Q comma epsilon. So here current state is P, and next state is Q, and the top of the stack is X, and next input is 1. So this is the production rule for pop operation. Current state comma top of the stack comma next state derives whatever the input. In this way we can represent the production rule for the pop operation from given transition. So and next from fourth transition, so that is del of P comma 1 comma X is equals to P comma epsilon, that is pop operation. So here current state is P, and next state is current state is P, and top of the stack is X, and next state is also P, and here input is X 1. So that's why P comma X comma P derives 1. And next transition, this is pop operation, that's why only one production rule can be generated. Next transition is del of P comma epsilon comma Z. Here D, E indicates just we assume production numbers as A, B, C, D, E. So that means fifth production, that is del of P comma epsilon comma Z equals to P comma epsilon. This is also pop operation. That's why we can mention production rule as current state P, top of the stack Z, next state is P, it derives input is nothing, that is epsilon. So this is the production rule for this pop operation. So till now we cover all, we are converting all transitions into production rules. Now we can write the whatever the context free grammar after whatever the grammar after converting from push down automata to context free grammar, that is G equals to VTPS, and we can mention what is meant by V, what is meant by T, what is meant by S, and what is meant by P. So these 13 production rules can be rewrite here. So then our problem will be completed. So this is the process of how to convert from push down automata to context free grammar. Thank you.